Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Time travel has captured human imagination for centuries, but what does modern physics actually tell us about manipulating time itself? The answer begins with Albert Einstein's revolutionary insights that fundamentally changed our understanding of reality. Before Einstein's theories of special and general relativity in the early 1900s, scientists viewed time as an absolute constant, a universal metronome ticking uniformly throughout the cosmos. Einstein shattered this notion, revealing that time is relative, malleable, and intimately connected to space in a four-dimensional fabric called spacetime. Special relativity, published in 1905, demonstrated that time passes differently for observers moving at different velocities. This phenomenon, known as time dilation, becomes pronounced as speeds approach the speed of light, approximately 186,000 miles per second. Imagine twin siblings. One remains on Earth, while the other travels to a distant star at 90% light speed. Upon the traveler's return, they would find their Earth-bound twin significantly older. This isn't science fiction. It's verified physics that GPS satellites must account for to maintain accuracy. General relativity, Einstein's masterpiece from 1915, expanded these concepts by incorporating gravity. Einstein revealed that massive objects warp spacetime itself, creating what we perceive as gravitational fields. Time runs slower in stronger gravitational environments, an effect called gravitational time dilation. Near a black hole's event horizon, time crawls compared to distant observers. This means time travel to the future is not only possible but inevitable. Every moment carries us forward through time's river. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Experimental evidence overwhelmingly supports these relativistic effects. In 1971, physicists Haffley and Keating flew atomic clocks around the world, confirming time dilation predictions with remarkable precision. Particle accelerators routinely observe short-lived particles existing longer than expected due to their high velocities. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, detects ripples in spacetime itself, proving Einstein's geometric interpretation of gravity. But these effects primarily enable forward time travel, moving into the future at different rates. The real question becomes, can we reverse time's arrow and journey into the past? This possibility requires examining more exotic solutions to Einstein's field equations. Theoretical physicist Kurt Gödel discovered rotating universe models that permit closed time-like curves, paths through spacetime that loop back to earlier moments. While Gödel's specific solution doesn't describe our universe, it demonstrated that general relativity doesn't fundamentally prohibit backward time travel. Understanding time's true nature reveals that our everyday experience represents just one perspective on a far richer reality. Time isn't the rigid framework we intuitively perceive, but rather a dynamic dimension that responds to motion and gravity. This flexibility opens theoretical doorways to temporal manipulation, though the practical challenges remain formidable. As we'll explore, several proposed mechanisms might theoretically enable backward time travel, each requiring extreme conditions that push the boundaries of known physics and engineering capabilities. While forward time travel through relativistic effects is well established, backward time travel requires exotic solutions that stretch our understanding of space-time geometry. Several theoretical mechanisms have emerged from general relativity's mathematical framework, each presenting unique possibilities and challenges for manipulating time's flow. Wormholes represent perhaps the most famous theoretical pathway to time travel. These hypothetical tunnels through spacetime could connect distant regions of the universe or different moments in time. The Einstein-Rosen bridge, derived from Einstein's field equations, describes a wormhole connecting two black holes. However, such natural wormholes would collapse instantly without exotic matter possessing negative energy density to stabilize them. Physicist Kip Thorne demonstrated that traversable wormholes, stable enough for travel, could theoretically exist if exotic matter with negative energy could prop them open. Creating a time machine from a wormhole requires additional manipulation. One end would need acceleration to near-light speeds, causing time dilation effects. When the accelerated end returns, it would be younger than its stationary counterpart, creating a temporal differential. Travelers entering the younger end could emerge from the older end in their past. However, this requires maintaining a stable wormhole across vast distances and time periods, a technological challenge beyond current capabilities. Cosmic strings offer another intriguing possibility. These hypothetical one-dimensional defects in space-time, potentially created during the universe's infancy, would possess tremendous linear mass density. Two cosmic strings moving past each other at relativistic speeds could create closed time-like curves in their vicinity. Observers following specific trajectories around such configurations might theoretically arrive at their starting point before they left. However, cosmic strings remain purely theoretical, and no observational evidence confirms their existence. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, describes a space-time geometry that contracts space in front of a spacecraft while expanding it behind. This configuration could theoretically propel vessels faster than light without violating special relativity, since the ship itself never exceeds light speed locally. Modified versions of the Alcubierre geometry might enable time travel by creating closed time-like curves. However, the energy requirements would be astronomical, potentially requiring the mass-energy equivalent of Jupiter converted to exotic matter. Rotating massive cylinders, known as Tipler cylinders, represent another theoretical time machine. Frank Tipler demonstrated that infinitely long rotating cylinders of sufficient density could drag space-time around them, creating closed time-like curves. Observers following helical paths around such cylinders could theoretically travel backward in time. Unfortunately, constructing a Tipler cylinder would require infinite length and impractical amounts of matter, making it physically unrealizable. Quantum mechanics introduces additional complications and possibilities. The many worlds interpretation suggests that time travel might create parallel timelines rather than paradoxes. Quantum field theory in curved spacetime reveals that exotic matter with negative energy density might exist in specific configurations, potentially providing the ingredients needed for wormhole stabilization. Recent theoretical work has explored other exotic scenarios. Closed time-like curves might emerge near rotating black holes called Kerr black holes, particularly in regions called ergospheres, where spacetime itself rotates. Some solutions involve cosmic strings intersecting with black holes or configurations of multiple black holes with specific angular momentum relationships. Each proposed mechanism faces severe practical limitations. The exotic matter requirements, energy scales, and engineering challenges involve dwarf current technological capabilities by many orders of magnitude. Moreover, many solutions exist only in idealized mathematical frameworks that may not reflect physical reality. Nevertheless, these theoretical explorations illuminate the rich mathematical structure underlying spacetime and time itself. Time travel to the past immediately confronts one of physics' most perplexing challenges: temporal paradoxes that seem to violate causality and logical consistency. These paradoxes don't merely represent philosophical curiosities, they pose fundamental questions about the nature of reality, free will, and the universe's logical structure. The grandfather paradox stands as the most famous temporal contradiction. A time traveler journeys to the past and prevents their grandparents from meeting, thereby preventing their own birth. But if they were never born, who traveled back to prevent the meeting? This creates a logical loop that appears to negate itself. Variations include the Hitler paradox, traveling back to eliminate historical atrocities, and countless scenarios where past alterations seemingly erase the time traveler's motivation for making the trip. Information paradoxes present equally troubling scenarios. Consider a time traveler who brings Shakespeare's complete works back to the 16th century and gives them to young William Shakespeare, who then publishes them as his own creations. Where did the information originate? The plays exist without any creative source, violating our understanding of causality and information conservation. Similarly, a time traveler might solve a complex mathematical theorem using future knowledge, then travel back to provide the solution to past mathematicians, creating an information loop with no true origin. Bootstrap paradoxes exemplify temporal, self-consistency problems. Objects or information exist in closed causal loops without clear origins. Say a watch given to a young person by their future self, which they later give to their younger self, creates an object that exists eternally within a temporal loop but was never manufactured. These scenarios challenge our understanding of cause and effect, suggesting that effects might precede their causes in ways that defy logical reasoning. The Novikov self-consistency principle, proposed by Russian physicist Igor Novikov, offers one potential resolution. This principle suggests that the universe's physical laws naturally prevent paradoxes by ensuring that any time travel scenario must be self-consistent. Events would arrange themselves so that time travelers cannot alter the past in ways that create contradictions. The universe would somehow conspire to maintain consistency, perhaps through quantum mechanical effects or unknown physical laws. Under the Novikov principle, a time traveler attempting to prevent their grandparents' meeting would inevitably fail. Perhaps their interference actually causes the meeting, or unforeseen circumstances prevent them from completing their mission. The principle doesn't deny free will, but suggests that free will operates within constraints that preserve causal consistency. This approach treats time travel scenarios like boundary value problems in physics, where initial and final conditions must be simultaneously satisfied. Quantum mechanics offers alternative resolutions through the many worlds interpretation. Rather than creating paradoxes, time travel might spawn parallel timelines or alternate realities. A time traveler preventing their grandparents' meeting would create a new timeline where they never existed, while their original timeline remains unchanged. This parallel worlds approach eliminates paradoxes by making changes that don't affect the traveler's origin timeline. Another quantum solution involves the concept of quantum consistency protection. Quantum fluctuations might prevent or counteract paradox-creating actions through probabilistic effects. The uncertainty principle could ensure that precise knowledge required for creating paradoxes remains impossible to obtain. Quantum mechanics' probabilistic nature might provide natural safeguards against causality violations. Some physicists propose that time travel scenarios might be physically impossible precisely because they create paradoxes. Stephen Hawking's chronology protection conjecture suggests that unknown physical laws prevent closed time-like curves from forming. Perhaps quantum effects near potential time machines become so extreme that they destroy the devices before temporal loops can be established. Recent work in quantum gravity and string theory has explored how microscopic quantum effects might resolve macroscopic paradoxes. Loop quantum gravity suggests that space-time itself possesses discrete quantized structure that might prevent paradox formation. String theory's extra dimensions could provide escape routes for information or causality that eliminate apparent contradictions. The paradox problem ultimately reflects our incomplete understanding of time's fundamental nature and the universe's logical structure. Contemporary physics research continues pushing the boundaries of our understanding of time, causality, and temporal manipulation. While building actual time machines remains far beyond current capabilities, scientists are conducting sophisticated experiments that probe time's fundamental nature and test the theoretical foundations underlying temporal phenomena. Quantum mechanics experiments have revealed fascinating temporal behaviors that challenge classical intuitions about cause and effect. The quantum eraser experiment demonstrates that quantum measurements can seemingly influence past events, though careful analysis shows that information never truly travels backward in time. In these experiments, photons pass through double slits, creating interference patterns. Later measurements on entangled partner photons can apparently determine whether the original photons exhibited wave or particle behavior, suggesting retroactive influence. However, the complete information needed to reveal this influence only becomes available after all measurements are completed, preserving causality. Quantum teleportation experiments, while not involving time travel, demonstrate instantaneous information transfer between entangled particles across vast distances. Teams at universities worldwide routinely teleport quantum states between laboratories, separated by hundreds of miles. These experiments reveal that quantum mechanics permits correlations that transcend classical space-time limitations. Though they don't violate special relativity, since no usable information travels faster than light. Atomic clock experiments continue refining measurements of time dilation effects predicted by relativity. The National Institute of Standards and Technology operates optical atomic clocks accurate to 1 part in 10 to the 19th power. These incredibly precise instruments can detect time dilation effects from elevation changes as small as 12 inches. Such precision allows researchers to test general relativity in previously impossible detail and search for deviations that might reveal new physics. Gravitational wave detectors like LIGO and Virgo have opened new windows into spacetime's dynamic behavior. These instruments measure gravitational waves, ripples in spacetime itself, created by colliding black holes and neutron stars. Each detection provides data about extreme gravitational environments where time dilation effects become pronounced. Advanced LIGO can detect spacetime distortions smaller than 1/10,000th the width of a proton, revealing the universe's most violent events. Particle accelerator experiments routinely observe time dilation effects in high-energy particle interactions. The Large Hadron Collider at CERN accelerates protons to 99.99999% light speed, creating conditions where time dilation becomes extreme. Short-lived particles that normally decay in microseconds survive much longer due to relativistic effects, providing direct evidence of time's malleability. Researchers are exploring exotic matter states that might possess the negative energy densities required for theoretical time machines. The Casimir effect demonstrates that quantum vacuum fluctuations can create negative energy between closely spaced conducting plates. While the energy scales involved are tiny, some theorists speculate that advanced civilizations might manipulate quantum vacuum states to create the exotic matter needed for wormhole stabilization. Black hole research has intensified following the Event Horizon Telescope's groundbreaking images of supermassive black holes in M87 and our galaxy's center. These observations provide unprecedented glimpses into extreme gravitational environments where general relativity's predictions become most pronounced. Near black hole event horizons, time dilation effects become so extreme that external observers would see infalling matter apparently frozen in time. Theoretical research continues exploring new time travel scenarios and paradox resolutions. Loop quantum gravity suggests that spacetime possesses discrete, quantized structure at the Planck scale, distances of approximately 10 to the minus 35 meters. This quantization might naturally prevent paradox formation by eliminating perfectly precise causal loops. String theory research explores how extraspatial dimensions might affect temporal mechanics and provide new pathways for information flow. Quantum computing research has revealed unexpected connections between quantum mechanics and temporal phenomena. Quantum computers can theoretically solve certain problems exponentially faster than classical computers, leading some researchers to speculate about quantum algorithms that might probe temporal relationships in novel ways. However, these investigations remain highly speculative and face fundamental limitations imposed by quantum mechanics itself. Laboratory experiments continue testing the boundaries between quantum mechanics and general relativity in tabletop settings. After examining the theoretical foundations, experimental evidence, and fundamental challenges surrounding time travel, what realistic conclusions can we draw about its future possibilities? The answer requires careful synthesis of established physics, speculative theories, and practical limitations that constrain even the most advanced civilizations. Forward time travel stands on solid scientific ground. Every moment carries us into the future, and relativistic effects allow manipulation of time's passage rate. Astronauts aboard the International Space Station experience time dilation effects, aging slightly slower than Earthbound humans due to their orbital velocity and reduced gravitational field. Future space travelers journeying to nearby stars at significant fractions of light speed could experience dramatic time dilation, returning to find centuries or millennia have passed on Earth. These effects become more pronounced near massive objects. Hypothetical explorers near neutron stars or black holes would experience extreme time dilation. 1 hour near the event horizon of a stellar mass black hole could correspond to years passing for distant observers. Such extreme gravitational time dilation represents nature's most powerful time machine, allowing travel arbitrarily far into the future given sufficient proximity to massive objects. Backward time travel faces far more formidable obstacles. While general relativity permits solutions containing closed time-like curves, implementing them requires exotic conditions that may be physically impossible. Traversable wormholes demand exotic matter with negative energy density in quantities that may violate quantum mechanical constraints. The Alcubierre drive requires energy equivalent to stellar masses. Cosmic strings remain hypothetical, and Tipler cylinders require infinite dimensions. Quantum mechanics introduces additional complications through the measurement problem and information conservation principles. The quantum Zeno effect demonstrates that frequent measurements can freeze quantum system evolution, creating temporal behavior that differs from classical expectations. However, these effects don't enable macroscopic time travel, but rather reveal subtle connections between observation, measurement, and temporal evolution at quantum scales. The grandfather paradox and related causality violations present logical challenges that may be insurmountable. While the Novikov self-consistency principle and many worlds interpretations offer theoretical resolutions, they require accepting either predetermined outcomes or parallel realities, concepts that strain our understanding of free will and reality's nature. Perhaps more fundamentally, Stephen Hawking's chronology protection conjecture suggests that unknown physical laws prevent paradox formation entirely. Recent developments in quantum gravity research hint at new perspectives on time's nature. Loop quantum gravity reveals that space-time itself may possess discrete granular structure at the Planck scale. This quantization could fundamentally limit the precision with which causal relationships can be established, potentially providing natural protection against paradox formation. String theory's extra dimensions might offer escape routes for information or causality that we haven't yet comprehended. Even if backward time travel were theoretically possible, the energy requirements dwarf any conceivable technology. Creating stable wormholes would require manipulating matter and energy on cosmic scales. Advanced Type 2 or Type 3 civilizations on the Kardashev scale, capable of harnessing stellar or galactic energy output, might possess such capabilities, but even then, fundamental physical limitations could prove insurmountable. The implications extend beyond mere technological challenges. Time travel capability would revolutionize our understanding of causality, free will, and reality structure. It would raise profound ethical questions about altering historical events and accepting responsibility for actions across multiple timelines. The knowledge that past events could be changed might fundamentally alter how we perceive meaning, consequence, and moral responsibility. Perhaps the deepest insight from time travel research comes not from its practical possibilities, but from what it reveals about time's nature. Time emerges as far richer and more complex than everyday experience suggests. It responds to motion and gravity, exhibits quantum mechanical properties, and maintains mysterious connections to causality and information that we're only beginning to understand. Current evidence suggests that while nature permits forward time travel through well-understood relativistic effects, backward time travel may remain forever beyond reach due to fundamental physical principles we're still discovering. The universe appears to protect its own causality through mechanisms we don't yet fully comprehend, preserving the logical consistency that makes science and rational thought possible. The quest to understand time travel continues driving advances in theoretical physics, experimental techniques, and our fundamental understanding of reality itself.